Hello, everyone. Welcome to the webinar for microchannel heat exchanger product. This is Chang Gao from SANHUA Microchannel Heat Exchanger Company. I'm very pleased to have this presentation about microchannel heat exchanger progress. I'm going to focus on the microchannel development for chiller heat pump and the application with low GWP refrigerants. This slide is about SANHUA and myself. SANHUA Group is the leading component manufacturer for HVAC and the refrigeration industry. The headquarters is located in Hangzhou, China. The revenue in 2020 is 4.1 billion euros. SANHUA Group has multiple business units, including the HVAC refrigeration components, microchannel heat exchangers, automotive components, and home appliances components. SANHUA has a globally footprint in US, in Mexico. We have the manufacturing factories, and we have a technical center in Texas, United States. About me, my name is Chang Gao. I got the PhD 15 years ago in heat transfer subject, and I worked since 2009 for SANHUA till now, and I drafted the Chinese first microchannel standards. Right now, I'm the member of HRI applied sector on behalf of SANHUA Microchannel Heat Exchanger. This is about the agenda of today's presentation. I will talk three topics. The first one is microchannel advantages and opportunities. The second one is microchannel chiller heat pump development. The third one is microchannel application with low GWP refrigerants. This slide shows about the microchannel categories. Currently, there are three kinds of microchannel heat exchangers. One of them is parallel flow. In the middle is a serpentine heat exchanger. That's typically for the refrigeration. And the right one is a bell tube heat exchanger. Normally, it's used for the air water heat pump, water tank heating. Still, the majority is a parallel flow, and it extends from standard condenser to the parallel flow evaporator, the oil cooler, parallel flow evaporator, and also the new style of heat pump microchannel. Microchannel heat exchanger is very familiar to the industry as a condenser due to its higher heat transfer performance, less refrigerant charge, less cost, better galvanic corrosion, comparable pitting corrosion. And as an evaporator, the copper fan tube heat exchanger has a formicary corrosion issue, but microchannel heat exchanger is all aluminum, so no worry about that. Also, the industry uses lots of aluminum fan tube heat exchangers to reduce the cost, but still that's challenging at the processing manufacturing. For example, the expansion and the lubrication is more difficult to the copper fan tube heat exchanger. And microchannel heat exchanger has very good advantages compared to the aluminum, more on the heat transfer performance and also on the manufacturing reliability. From the heat transfer perspective, microchannel has advantages to fan tube heat exchanger. At the tube side, the port microchannel is quite small, around 1 millimeter, so the tube side heat transfer coefficient is higher. At the L side, there's no tube blockage, and also the wavy fin has better heat transfer coefficient. And what's more, fan tube heat exchanger has this mechanical expansion, so there's contact thermal resistance. But for microchannel, it's all brazed, so there's no thermal contact resistance. This is a heat transfer model comparison of both heat exchangers. Microchannel heat exchanger has about 90 overall heat transfer coefficient, about 2.4 times of a fan tube heat exchanger, and the L side microchannel has about 2 times of fan tube heat exchanger coefficient, and the contact thermal resistance fan tube heat exchanger ratio is about 6%, but the microchannel is almost 0. Microchannel heat exchanger has a wonderful application potential and the background of global environment policies. Paris Agreement called for the temperature rise control within 2 Celsius degree, and the Kigali Amendment defines 18 HFC refrigerants to be controlled, including R3134A and R32. Let's see the Kigali Amendment schedule, the HFC phase-out impact. If we don't take the phase-out action, we will see the CO2 consumption still goes up until 2035. And if we take different levels of action, we will see the trend conversion from up to down. By the Plan C, this is the most stringent control. By using widely low GWP refrigerants, we will see the CO2 consumption sharp drop before the 2035. And by the statistics of JRAIA, currently globally is the air conditioning industry is using A2L low GWP refrigerants, especially in Japan and in Europe. The left chart shows different groups defines soon or late HFC phase-out schedule, and Europe is leading the HFC phase-out by the F-Gas Act, and that results in the fact the HFC tax by refrigerant will double in the coming 5 years. So OEMs in Europe is suffering the cost of HFC refrigerants, and microchannel heat exchanger can play a key role to reduce the application cost. The second part is about microchannel chiller heat pump development. Heat pump is a renewable energy heating technology widely used in globally, but microchannel heat exchanger has not been widely used as a heat pump outdoor condenser. Let's see what is a roadblock to microchannel heat pump. This animation shows that heat pump normally is used in the mild warm and mild cold region, and heat pump right now using 2 ratings. One is the COP, that is typical for commercial heat pump and some of the hot region. Another one is a residential product using the APF and the HSPF to rate the overall performance. And the frosting condition performance plays a role in APF and HSPF. Microchannel heat exchanger is typically used as a condenser in the cooling only unit with a horizontal tube design. But when it's used as an evaporator, it has difficulties at the refrigerant distribution, water drainage, and frosting performance. SANHUA developed a proprietary heat pump with a vertical design. It achieved the compactness like a condenser, and also get acceptable distribution, water drainage, but the frosting performance is not as good as a fan tube heat exchanger. And these years, we are upgrading the design to achieve a better distribution, better water drainage, but the frosting performance is still challenging to microchannel heat pump. Let's see the iteration design of microchannel for the heat pump. Previously, we used the 20 mm microchannel tube design to compare to the 1.5 row 9.5 mm fan tube heat exchanger. The rated cooling and the heating performance are very close, but under the frosting condition, the green curve is microchannel. The peak points are very close, but the deterioration of a microchannel is much faster than the fan tube heat exchanger design. And recently, we developed the microchannel new design to gain the performance under the frosting condition. And this chart is from the enthalpy loop testing. We tested the prior art design and the new design under the frosting condition. The blue one is prior art, the current design, and the black curve is a microchannel new design. We can see that capacity keeps flat for quite a long time. By the renewed technology we designed for the chiller heat pump units, this is a unit of 100 kilowatts chiller heat pump using R410A refrigerant, and the coil size is 2.1 meters long and 1.2 meters height. The baseline fan tube heat exchanger is a 4-row 7 millimeter, and the fin density is 12 fin per inch. For microchannel, we use one-piece folded coil with SANHUA proprietary tube bending technology, and it uses 2-row 20.6 millimeters tube. The tube height is 1.3 millimeter. We compare the coil weight and the internal volume of both heat exchangers. The advantage of microchannel is significant. Compared to the fin and tube heat exchanger, microchannel's weight can reduce by around 44%. And for internal volume, the reduction is around 50%, almost half. Let's see the performance comparison between the both heat exchangers. We firstly tested the coil-only performance as a condenser. The left chart shows the capacity comparison of microchannel to fan tube. Microchannel is 46% higher than 4-row fan tube heat exchanger. The right chart shows the outside pressure drop. Microchannel heat exchanger is about 4% higher, but generally it's the same level. Then we compare the performance as evaporator. This is still the coil-only performance testing. The left chart shows the capacity comparison. Microchannel heat exchanger is about 13% higher than the 4-row fan tube heat exchanger. And the right side is about outside pressure drop. A microchannel heat exchanger is about 12% lower than the fan tube heat exchanger. The next item is about charge. Charge is quite critical to the new A2L refrigerant system design. So we need to find the difference between microchannel and the fan and tube heat exchanger. Because we don't have the unit in-house laboratory, so we found a new way to test the charge for the coil only. Because condenser holds more refrigerant than the evaporator, so we measure the refrigerant charge after the condenser performance testing. And we added 2 valves in the inlet and outlet pipeline of the coil, and we used the weight method to get the refrigerant charge. So left chart shows the difference of both heat exchangers. The charge advantages of microchannel is quite significant. Microchannel reduces about 76% less refrigerant. The screw chiller normally uses R134A as the refrigerant. So we designed the coil also for the air-cooled screw chiller. This is a unit with 130 kilowatts capacity. The coil size is the same as a 14A coil. The fan tube heat exchanger is 3-row 9.5 mm fan tube heat exchanger. The fin density is 12 fin per inch. For microchannel, we used the same design as the 14A, so it can be a standard coil for both applications. For this screw system, we tested the coil-only performance. As condenser, it is not a concern, so we tested the coil-only performance as evaporator, because in R134A system, the performance is sensitive to the internal refrigerant pressure drop. We defined 2 evaporating heating conditions, and we tested the coil-only performance. The target is defined by the customer, and we tested the evaporator capacity. Both conditions, microchannel is about 6 to 16% higher than the target. For the system level, we validated the microchannel performance in the modular scroll heat pump system. This is a 65 kilowatts modular heat pump, very popular in China. The original fan tube heat exchangers are 4 pieces, 2 in one side, another 2 in another side. So they formed the V shape. We designed the 2-row 20 mm microchannel design. Still the 4 coils to replace the original 4 fan tube heat exchangers. This table shows the parameters of the system. Photon A system refrigerant, heat exchanger size the same, cooling capacity, heating capacity, and about the fan tube heat exchanger parameters. So look at the system testing results. The left two charts is about the cooling performance. Capacity of the cooling microchannel heat exchanger is a blue chart. It's almost the same as a fan tube heat exchanger. The cooling rating ER is 1% higher than the fan tube. The right two charts is about the heating performance. Microchannel capacity is 99% of a fan tube, and the heating COP is 1% higher. So generally, microchannel is very close to the fan tube at the rated cooling and heating conditions. We also tested the frosting condition performance. This chart shows about the comparison of a fan tube heat exchanger and microchannel condenser. In the frosting condition, that means the dry bulb temperature 2 Celsius degree, wet bulb 1 Celsius degree, and this is the typical cycle time and the capacity we put together. The green one is microchannel. It's pretty close to the fan tube heat exchanger and much longer than the previous design. So we calculated the average capacity. You can see the microchannel is about 96% of a fan tube heat exchanger. The frosting cycle time is very close, 3 minutes shorter, and the defrosting time is almost the same, 4 minutes, and the COP of the cycle is about 98%. So overall, the new microchannel heat pump solution can reach close performance at defrosting cycles. The audience may want to know how good microchannel can drain the water during the defrosting process. We put several pictures of different defrosting time. The first picture is about 1 minute after starting of the defrosting. We can see that there is still white frost on most of the coil. And 30 minutes later, we can see that the frost is only at the bottom of the part, and the other parts we see no clear frost. And 30 minutes later, we checked the bottom of the coil. We don't see the white frost, and the fin is getting wetted. And 30 seconds later, when we check the fin of the bottom coil, we see the fin is clear and dry. So there's no little water retention on the fin. And the new microchannel heat pump design defrosts fast. For heat pump, when the environmental temperature gets down, it's getting difficult to match the heating capacity and the heating load. But luckily, when the environmental temperature gets down, The absolute humidity is also getting quite low, and you will not see quite frequently the frosting and the defrosting on the heat exchanger. So we did the comparison testing of microchannel and the fan tube heat exchanger at the -16 ultra low temperature environment that is typical for Northern Europe and Northern China. And we recorded the capacity along the time. And we found that microchannel heat exchanger and fan tube heat exchanger both don't defrosting even for 5 hours. And microchannel always keep 11% higher capacity than the fan tube heat exchanger. So that means microchannel heat pump can continuously exert the heat transfer advantage in the ultra-low temperature environment. So that is the progress of chiller heat pump microchannel development. And right now we are working with some selected OEMs for microchannel application. And hopefully we can see the product in the near future. So the third part is about microchannel application with low GWP refrigerants. Because microchannel heat exchanger can fully utilize the charge advantage for the low GWP flammable refrigerants, the industry is thinking about to redesign the system using microchannel. But the first question would be, how would be microchannel performed with low GWP refrigerant transition? So we designed the horizontal flow coil and the vertical flow coil for the performance verification. The horizontal flow coil is a typical style for the cooling-only condenser, and the vertical flow coil is typically designed for the heat pump. It can work as the evaporator as well as the condenser. Here is the result of the microchannel coil performance with low GWP refrigerant. First, on horizontal coil, we present the heat capacity and also the refrigerant pressure drop. Compare the R32 and the R14A. So the left chart shows that the heat capacity of R32 is almost equal to R14A. The right chart shows that the refrigerant pressure drop of R32 is lower than R14A because of the mass flow of R32 is lower. This slide shows the microchannel performance with low GWP using the vertical coil. So the left chart shows the heat capacity, the right chart shows the refrigerant pressure drop. And for this vertical coil, we tested 14A, 454B, and 32. So the result shows the heat capacity of R32 is higher than 14A. And the 454B capacity is a little lower than the 14A. And look at the refrigerant pressure drop. The 32 and the 454B are both lower than the 14A because of the mass flow. Both are lower. This slide shows the refrigerant distribution characters in the vertical coils and horizontal coils. In the vertical coils, the refrigerants come to the top and come out at the bottom with different refrigerants. There's no big difference, and the thermal picture looks quite uniform. For the horizontal coils, there are two circuits. So the refrigerants comes in from the top and then comes out at the bottom. Also, for 32 and R14A, there's no big difference. Another question the industry cares is how microchannel heat exchanger can be compatible to the low GWP refrigerant. So in SANHUA, we did the compatibility testing with the quite popular refrigerant R454B. We used the high temperature autoclave to hold the specimens, and we set the temperature is 150 degrees C. The testing is under 1.7 megapascal for 14 days. There are 4 groups of materials. A is the copper aluminum tube and 3102 MP tube. B is the stainless steel copper pipe. F is the transition block copper pipe. And G is the 3003 manifold. This slide shows the compatibility results of R454B with microchannel components. So after 14 days testing, we poured out the specimens and cleaned them and took the picture to compare to the specimens before testing. The result shows compared to the appearance of the specimens before testing, the surface of all samples have no obviously change after 150 degrees C aging test. Also, we checked the oil lubricant after the testing. The POE oil has color change after aging testing, especially in the results which contains copper. But overall, compared to the standard testing for other refrigerants, there's no big difference for R454B with the traditional 14A and the R22 refrigerant. The low GWP refrigerant R454B has been announced by some big OEMs as the next generation product refrigerant. So in SANHUA, we did the benchmark testing with R14A and the 454B. It's based on the 3-ton AC unit, typical US residential style unit. The indoor used the A coil and the outdoor used the C-shaped coil. And we also make the microchannel A coil and the C-shaped outdoor coil. The right side is a comparison of the capacity, EER, and the refrigerant charge. Look at the capacity. The fan tube with 14A refrigerant is a baseline. And when we change the heat exchanger to microchannel, on both A and B condition, we can get at least 5 to 11% higher capacity. And when we change the microchannel, we can get the efficiency ER increase is very significant, is 8 to 12% higher. And when we used the 454B to drop in with microchannel, the capacity is a little lower than the 410A microchannel. But look at the ER, 454B with microchannel is higher than 410A microchannel. When we look at the refrigerant charge, this is a quite significant advantage. When we change the heat exchanger to microchannel, we can get about the 33% less charge. When we further use the 454B to drop in, we can get another 9% less refrigerant charge. So totally compared to the baseline, we can get about 42% less refrigerant charge. So based on the result, we are confident that with microchannel, it can provide very huge refrigerant benefit. This is a business model for the North American air handler units. The market is about 7 to 8 million air handlers. And if we use a microchannel, roughly estimation, by replacing the indoor, we can reduce 20% less refrigerant, and by outdoor replacement, we can get 30% less refrigerant charge. So totally, we can get about 50% less refrigerant charge by microchannel replacement. And let's assume the refrigerant cost R410A is $2.4 per pound, and the R454B is over $10 per pound. And roughly, if the volume is 800,000 units, we can get the maximum estimated refrigerant saving is $30 million per year. And the CO2 emission reduction would be 5.84 million tons. So microchannel can play a very great role to reduce the CO2 emission and the new low GWP refrigerants application costs. So that is all about this presentation. Thank you.